So this file basically derives the equations of motion of the passive walker. It has both parts to it. There is a single stance and then there is foot strike. I'm just going to run this first and let it basically produce its output, and then we'll go through a little bit of the code. Okay, so as part of this, you've done the homework on writing the equations for some harmonic motion previously. So it's going to be an extension of that. Essentially, you define position vectors using the same R matrices I wrote down in my derivation. Okay, eventually get the position. So xc2, for example, is the position of the x position of the foot, the swing foot, in fact. That's the y position of the foot, position of the center of mass, and so on. Okay, and that's probably the most tedious part of this whole derivation. Once you do that, velocity is very easy. It's basically using the Jacobian, or if you want, you can take the time derivative. Okay, this is something I wrote down. Now we go to the part where we get the kinetic and potential energy. So before we can do that, I just find the position of the center of mass G1, G2, and of the point mass on the hip with respect to the world frame, because remember we are on a ramp, so I need to use the slope to get that. And then we have the kinetic energy, which is half mv square for each mass, half I omega square for each leg. And then we have the potential energy, and then t minus v is the Lagrangian. So everything here after here is straightforward, which is basically using the Euler-Lagrange equations, using the same formula as I wrote down earlier, and then extracting out the A matrix and B matrix. The A matrix is basically nothing but uh, the mass matrix. A is the mass matrix. And then so all I need to do is I need to find the acceleration. In this case, it's theta1 double dot and theta2 double dot. That comes from inverting this A matrix and multiplying with the right hand side. The right hand side consists of Coriolis force and gravitational force, which all of it which is clubbed in on the right hand side. Okay. And then this is the part which goes for the heel strike stuff or the foot strike stuff. Foot strike. I need a few Jacobians for the swing leg, and I need the Jacobian. Well, this is not Jacobian, but this is the right hand side. This is all straightforward once you look at the equations which I wrote down. I find the Jacobian, I find the A matrix, which is the same as the M matrix in that uh, in the derivation I wrote down. And basically, what you need to compare my notes with this is to look at these four lines. Okay, basically this is the A matrix, which consists of A minus J, and this is something which I derived, and then there's the right hand side. Okay, and then here I do the additional step of doing the swap. So I already do the plus the velocity. In this case, the velocity 1 and plus velocity 2 angular velocity, which gives me the new angular velocity after foot strike, and then the same thing for angular velocity of the other leg. Okay, so what this produces is these set of equations, okay, which I need to copy paste in my single stance. So this was something I would copy paste just like my previous derivations. And then we have this set, which is the heel strike, which again I'll copy paste. Okay, so before I write the equations, let me just give you an overview of what I'm trying to do. This is by far the hardest part uh, to really teach how to do this, because it's more than just for following a formula. It's basically uh, something which you will develop as you start doing this programming. Okay, so what I'm going to do is I'm going to have a one-step function which does the following. It does single stance. Okay, using the equations I just derived. Then it does detect ground. I'll call this function actually collision. And then it will, the third thing it will do is it will do foot strike. Okay, so to this file, to this function, what I can do is I need an initial condition. So let's call that Z0 initial condition. So I'll input the initial condition to one step. And you want to have the initial condition such that it starts off in this position, right? When both legs are on the ground. So this is C1, this is C2, and this is going to be theta 1, a better figure. Theta 1, and let's see, this is negative theta 2. So I'll have some value, let's say theta 1 is zero point 0.2, and then theta 2 would be minus zero point 0.4. That's just initial guess to get this started. So once you put this initial condition to this, uh, it'll throw out uh, the state theta 1 dot, theta 2 dot, and it'll basically be time, so 0.001 and so on, basically some timestamps and the angle velocity. So once I have this, I can then take this in animate or some animation routine where I'll take the theta 1 value, theta 2 value, and then do some animation of the robot. Okay, and this will help me to debug my code and see where I'm making a mistake. And I say that this is how you do it because getting these workers to work is a bit of trial and error. So these initial conditions, I have no idea if they work. So this is just theta 1, theta 2. I also need to specify theta 1 dot and theta 2 dot. And so we'll get sort of an intuition by looking at an animation. So I always suggest people that before you do anything more fancy, try to do a simple animation. Okay, and what I'll do is, in order to write this one step, I will use the one bounce code. Okay, the one bounce code is something I wrote for simulating a bouncing ball. Okay, so I'll use that as a starting point. In fact, I like doing this where I take a code which already works and it's debugged and then slowly change things inside that so that it is useful for a different purpose, and it works much faster to do it that way than to write a code from scratch. Okay, so this is my uh, approach. Let's see how far I get doing this today. Bounce code from 2 classes back, and I'm going to call it passive walker class, and hopefully get this going such that I'm able to get a first few steps of this walker. Okay. Okay, so let's start with this file. Let's call this, instead of getting ball main, let's call it pdw. Uh, then we have uh, one bounce. Let's call that one step. And then we have RHS. Let's keep it as its contact is fine. We'll also need a file for um, foot strike. Okay, we'll create that later on. But let's look at pdw main. Okay, so I need to modify this. What I'm going to do is, instead of writing everything from scratch, I know a few set of parameters which I have used in the past, which I know sort of work. And so I'm going to basically get rid of all of this and then put those. So this is basically the mass at the hip, the mass of the legs, the inertia, length. This is where the center of mass of the leg is from the hinge joint. Gravity is 1. That's because I've non-dimensionalized everything with gravity. Okay, and then the slope is 0.01. Okay, so what I need to do now is specify initial state q1. Let me call it theta 1 equal to, I think I wrote down 0.2. Um, theta 1 dot, let's specify, so theta 1 is going from positive to a negative value, so it better be negative. Let's try point 0.1. Okay, then theta 2, I said it should be 2 times theta 1, because we start from the point of foot strike, and then theta 2 dot, let's just put 0, and then we'll put some number later on. Okay. Okay, so what I need to do is I somehow need to call this. So let me comment all this out. I'm not going to use this. We comment all this out because I have something different in mind. Okay, so what I'm going to do is next pack all these things in a variable z0. So I like to put theta1 followed by theta1 dot, and then theta2 dot, and these are basically the initial conditions. Okay, I'll take these initial conditions, integrate over one step, and my goal is to make an animation, see if that leads to a successful step. Okay, so then I need to write one step. I intentionally wrote it such that it outputs the z, which is the table of all the angles as a function of time, and then the time, of course. And then input to this would be the initial state. I also need to send to it walker, which is my object, which basically has the mass and so on. Okay, so now since I got this, now I'm ready to try to write one step. So let me open that. One step. Okay, so here I'll call it one step, and since my input is t0, it should be z0, and then of course walker. Okay, now this is going to be the file detect contact. Let me just open that also. So contact, or I'll call it, since let's just call it contact. This looks fine. Tolerance is okay. Usually I recommend higher tolerance. Let's put 10. You cannot go above 10 e raised to negative 14 because that's the tolerance of this machine, or sorry, MATLAB. Okay. Now with RHS, I need to integrate from T0 to T0 plus dt. Then there's the initial condition Z0, and then I need to pass on walker. Okay, and then output, since I'm sticking to so let's see, here I have output as z and t. So what I want to do is here is just change this to z first and t second, and then this is produced. ODE45 produces, it produces t comma y, so time and the state. So I need to write a t comma z, although I'm sending up z comma t. And let's just forget this for an instant and forget this. Okay, so right now I'm just trying to integrate and get the result t and z. Okay, so there is no foot strike right now, but I do stop when there's contact. Okay, so let's code single stance, let's code contact, let's set animation and see if we can get it to do one step. Okay, so let's open up RHS. Okay, and this one looks very simple, but let's change this to walker. And I do not need all this. I just need to change based on passive walker derived. So let me run this code. Okay, now here I need to only copy paste this part. Take this part, copy it here. Okay, and then output is basically, it should be z dot. Okay, it's basically a derivative of z. What is z? Z is q theta1 is z1, theta1 dot equals z2, theta2 is z3, and theta2 dot is z4. Okay, that's my input. Now let's look at the output for a second. What's alpha? Alpha is two things. Alpha has theta1 double dot, theta2 double dot. You can refer to the notes on how these alpha comes. Basically comes from doing the Euler-Lagrange equations, which gives me the rate of change of velocity, which is acceleration. So if I want to find z dot, which is the rate of change of z, what is z? Z is theta1 dot, theta2 dot. Okay, so z dot is the rate of change of z, and so it has to be theta1 dot, which is the derivative of theta1. Then it has to be theta2 double dot, sorry, theta1 double dot. What is theta1 double? I should have written down here. Theta1 double dot is alpha 1 and theta 2 double dot is alpha 2. So then that becomes my second argument, and then the third argument is the rate of change of theta 2, and then theta 2 double dot. Okay, now it wants it to be a column matrix. So I need to take the transpose, and so this is the output, which is great, and this is the input. Okay, I still need to unpack the mass and c and so on. Let's just do that. So I equals walker dot I, m equals walker dot m, capital M equals walker dot m, and c equals walker dot c, and then L equals walker dot L, and I think there's G, which is walker dot G, and then if you want gamma is walker dot gamma. Okay, I don't think there are any more variables. I think I've covered all of them. Okay, so all this does is takes in dz and then I, and then finds, and I think I'm missing something here. Okay, so I think I'm all set here. This function is done. I basically have taken the inputs, found out the acceleration, packed them into outputs, z dot, and I'm done. Okay, now contact. So let me change this. Oh, you know what? Let's skip this for a second. Let's go to one step here. Let's just skip this altogether. Let's debug it one at a time. Let's just not worry too much about the contact. Okay, so now this is only going to do integrate equations for single stance. Okay, well, let me run this and see if it works, and then I'll do animation. So run this. Okay, so first complaint, line 8, not enough input arguments. Let's see, main at 11, okay, which is this, and then one step. Okay, you can see here I wrote T0, Z0, walker. So there are three inputs, but here there are just two. So I need to create one. Let's just say T0. T0 equals 0. Okay, it should hopefully work now. Okay, so I have not defined omega. Okay, so I did a mistake here of defining it slightly differently. This should be, I did not call it theta 1 dot, really. I called it omega 1. And then I called this omega 2, and so that's why I was complaining. But if I change this to omega 1, omega 2, then I need to go here and then change this to omega 1 and omega 2. And then the other things are fine. Let's run this now. Okay, so no complaints, it worked. Okay, now there's no way of guessing what might be going on behind the scenes. So what I suggest is uh, uh, let's do an animation. Okay, so let me pull up the animation part 1 second. Okay, so animation. And then if you like and keep it white ball, looks like there are too many things to change here, but I definitely need to change this. Okay, let's just rename all the y alls to z alls because we've used z for everything. Okay, that looks good. Okay, so this is basically a place where we are basically interpolating. So normally when you have data coming from OD45, you get maybe 1,000 data points. But if you start animating with 1,000 data points, the animation will become very slow. So this basically takes the data points and sort of makes it sparse. That way the animation looks more realistic. It, however, requires this FPS, which I have not defined. So what I'm going to do is I'm going to define movie.fps in my code. So let me call this walker.fps. I need to define this, and I'll have to put like a value of 30 and then change it as per your needs. Let's just go here and just make it 30, and then we can change it later. Okay, now animation. let's call this Z because we're only dealing with Z. Z, 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 though I don't need this, I think. Okay, let's not worry too much about writing a movie file. I'll comment this out, I'll comment this out, but you can change that later on. Okay, so this is interpolation. Now let's just do the plotting. Okay, so first of all, what I need to do is, so see, there's a way to do this on over here without writing it. There's xh, yh, which is the leg, and then there's going to be one leg, and then another leg. Let's see if we can do this. It is the backslash. Okay, backslash. Okay, and then line, line. Okay, so this is basically just a caricature of the robot. We have on this one, we have C1 and then we'll have C2. Okay, and what I need to do essentially is draw a line from C1 to XH and then C2 to XHYH, and then I have the thing going, right? So then the the easier way of doing this is actually to keep track of the hip XHY. Let me just quickly check something. Okay, so what the easiest way of doing the animation, so one way of doing the animation is basically you keep track of the C1, which is the leg on the ground, and then you keep track of, well, you draw a line from here to XH and then XHYH and then draw a line from XHYH to C2. But what I found is that it's much easier if you actually keep track of XHYH, which is the hip point, and then from there it's much easier to write the coordinates of C1 and C2 because you know the angle is theta 1, theta 2. So instead of keeping track of C1, which keeps changing, right, as the foot hits the ground, I keep track of XHYH and I use that to draw the legs. So that additional step I will do the step now, which is basically I will, for Z all, I have theta 1, which is Z all 1. Sorry, it's the first column. And then I also keep track of theta 2, which is Z all the third column. What I'll do is, and so of course theta 1 dot is for second column, and then theta dot is the fourth column, right? This is all fine. What I'm going to do is I'm going to try to get the XH and sort of save the XH beforehand in the simulation and then try to populate this here. So I'll call that fifth one because the fourth one is taken, and then YH is going to be the sixth one. So I need to supply this to this code and I need to do it externally to this. Okay, now you could do it internally, but I recommend doing it externally. So let's just see if we can get these values from PW main. Okay, so what I'll do here is before I call the animation code, which is right here, let me move this up. Okay, I need to get XH and then YH. So there's a formula for XHYH, and it's actually not, it's actually sitting right here. If you see this derivation, I've actually defined what XH and YH is. So let me just produce that. XH, YH, and I can put a breakpoint here. Okay, so this is xh and this is yh, and the way I wrote xh is basically I use the c1 to be x, the position x coordinate of c1, which is the contact point, to be x, and y, and really that's an arbitrary number. You can start it from anywhere. So I'm going to take this part and then quit this, and then go over here, and then write. If you want, you can write this way, or you can put a 0, because this is basically specifies the starting point. Let me just put minus L sine theta 1 and then L cosine theta 2. The reason I put this, I ignored the x and y, is because I just want to assume that the C1 is the place where I start the robot, is basically the origin. Okay, so now there's no theta 1 really, but theta 1 is a part of z. So z has theta 1 dot, theta 2 dot. So what I need to do is I need to take the z value and then get the first element, and then same here. So what this has done effectively is it has given me all the xh and yh for the entire simulation. Okay, and then I need to define this as walker.l, because I've not defined L as independent variable. Walker.l. Okay, and so now what I can do is z all is going to be z comma xh yh. Okay, let's just see what's happening here. Too many things going on. Let's just uncomment this and see what z all is. So I did the simulation. This is the output. This is z all. So you can see there are 6 columns. The first, sorry, I got distracted. I thought there was a chat, but there's none. Okay, so the z all has 6 columns. The first 4 columns correspond to theta 1 dot, theta 2, and theta 2 dot, and then there is xh and yh. Okay, you can see that yh, which is the height, is almost about 1, right? It basically goes 1 and so on. It should be 1 and then goes down. Anyway, so I have the right thing. I just have to send it now to the animation code. So now this is the right thing. It goes in there. I already got xh yh, and now what I'm going to do is I'm going to use this to do my animation, which I've shown over here. All I need to do is draw lines from xh to c1, xh yh to c1, xh yh to c2. So let's do that. Okay, so hinge, which is the center point, is, so let's just do that first. Hinge 1 xh 1 yh 1. So this is basically the xh is what I'm going to draw. I'm just going to put a dot over there. Marker face color. So this is just setting the color of the face. It's K, which is black. Actually, I forgot. It should, when I do a plot like this, I should say KO. KO means that it's a black circle with, the circle is denoted by O and K is the color. The face color is the color of the circle. It's going to be black. And then I need to put a marker size. And let's just put 15 or 20 or something like that. Let's put 10. Let's just do a small value first. Okay, so that's going to give me the xh. Now let's just try to draw a line from xh to c1. So let's just get the coordinates of.
Real quick, I think you may have left out some apostrophes on marker size.
Oh yeah, good catch. Thank you. Okay, so let's get the coordinates of c1. C1 is the stance foot. So the angle made by xh and xh yh and c1, let's just call it h. Okay, h and c1 is basically theta 1. So all I need to do is take the xh and to it add L times sine theta 1. Now sine theta 1 is basically, it's an array, so I need to get the ith element, right? Hold on. Okay, I should take this. So this is basically the uninterpolated values, but then I interpolate them. So I need to move this from here to right here. So that way it's only dealing with the interpolated values. Okay, so now once I have it here, I just need to take the first value. So that's the x position of C1, and then y position of C1 is YH minus L times cosine theta 1 I comma 1. Okay, that looks okay to me. So this basically comes from the trig, but you can also find this from the derivation. If you go and uncomment the position of xc1, which, well, I don't think I have xc1 quite that way, but it basically is, if you can find xh, then you can find xc1 by doing subtracting xh, subtracting so let's see, xh. I wrote down this earlier. Let me just put it down there. And then we have xc2. Okay, so this is basically giving me the coordinates of xh given the position of xc1. So if I were to find the coordinates of xc1, all you need to do is you need to move this part to the other side. So it's going to be xh plus L sine theta 1, and that's precisely what I have over here. And similarly, if you want to find the coordinates of yc1, you need to take this L cosine theta and move it to the other side. So it's going to be YH minus L cosine theta 1, and that's precisely what I have over here. So you can actually use the derivation to get this. So I'm going to just complete this, right? xc2, it's xh plus L times sine theta 1 I comma 1 plus theta 2 I comma, okay, and then the YH is, YC2 is simply YH L cosine, okay, this, and the negative sign here, similar to the other one. Okay, so now we are all set. Let's just draw a line between xc1 and I need to draw a line from xh to c1. So that's going to be line xh xc1 yh yc1, and then I need to put some color. Let's just put if you like red, and then if you want a line width, make it thicker line, then line width 2 will do it. Okay, so that's the one line. The other line is going to be xh and xc2, and then yh and yc2. So that's fine. And then what will happen here, however, is that we need to sort of delete this line and refresh it. So I'm going to call this h0, and this is just an identifier for the plot command h1 and h2. So what I do is I create this basically draws the dot and then two lines, and then I say pause for some time, and then I say delete h0, delete h1, delete h2, and then I believe I need to say somewhere, hold on, okay, so in this bargain I forgot to draw a horizontal line corresponding to the ramp. So I just do that quickly. Line, say minus So x is minus 2, plus 2, 0, 0, line width 1, color k, and this is just drawing the ramp. Okay, hold on, that's just saying that don't delete that line, and I think that's it. Let's see if this works. So I think I've written down all the code I need to get this to do animation. Okay, function not defined, line 22. T all. Okay, T all is the same as T, so I could just write it as T all is undefined variable L. So I'd better define this in the animation file. So I go here and we'll define L as walker dot L. Okay, let's just run this. Invalid argument. Okay, so let's see, help line. I think I'm using the line command incorrectly. So x, y, z, and then I need to name value pair. So what mistake I'm doing here is I can't just say, I need to say something like this. So let's get rid of, say it this way. So since I wanted red, call it red. Okay, now let's run it. I don't know why it's drawing an arc, but let's see if we can debug this. Animation. Okay, so let's just get rid of this and this first to start with. Let's see what we get. So we just see a dot. It doesn't seem to be moving. Okay, animation. Okay, I think I know what the problem is. So here I have got xh and yh, which is basically all the variables, but then here instead of taking each value and plotting it, I'm just taking the entire array. So I just need to do this I comma 1. And then the same thing here. Then extra. Okay, let's see if this works. Okay, it looks like it's doing something predictable, but just put the lines and see what it is doing. Okay, let's run this now. Okay, weird. Okay, so it's actually drawing the lines and not erasing them. That's because I uncommented this out. Okay, and I also noticed that I need to make my axes equal. So let me make the axis, let's say -2, +2. I forgot how the axis to use axis. So it should be, let's see. Okay, x min, x max, y min, y max. So -2 +2. And so this is going to ensure that it's scaled properly. And I think I need to put this before pause. Just do that. Okay, let's run this. Okay, that just looks weird. It looks like it's doing something, but the animation doesn't look right, at least the simulation. Okay, so there's something to do with my initial conditions. Theta, okay, so that's the problem is here. My theta2 is actually should be negative. You can see that the swing leg was in front of the stance leg, so I need to put a negative, and maybe it'll work now. You can see it's falling backwards. Okay, that means there's not enough velocity to it. Why is it so jarring? Let me make it 0.05 and we can Watch it again. That's too slow. Just quit this animation. I think this is fine. Let's just make this 15. It'll hopefully work better. Wait, that's weird. Okay, that just shows that I did not launch it with enough speed. So the way I can launch it with enough speed is basically changing this one. This is basically the velocity of the stance leg. So let's just make it 0.5 and see what happens. So you can see it's falling now in front. So that's not going to help. Okay, so maybe we need to make it somewhere in between. So minus 0.3. Okay, that looks a little better. You can see. So it looks like it's almost there. So I want to avoid this thing where it just disappears at the end, and that's because I'm always making it delete. So what I can do is to fix that, I just tell it that if I is less than, so it goes from I to length interp. If I is less than length interp, which is it's not the last value, then you do do delete, else don't do anything. So I just say end. Hopefully this will fix it. So now if you run this, I did a mistake there. Length interp. It was t interp. Yeah, it'll work now. Okay, there it is better. And then it goes, and then looks good. But now it did not go away. So that's how we can check. So now it looks like it's doing the right thing. Let's try to introduce the collision condition now. So one step. We had deleted this. Okay. We go to contact, and then we said that the G-stop condition is, I think it's θ1. So we have Z and then Walker, and what we need to do is get θ1, which is Z1, get θ2, which is Z2. By the way, I forgot to tell you one thing. I should have checked this. So let's get back to this, okay, and run this, and you see that it's actually doing it's doing fine. But this is actually a problem, because when I integrate this, I should try to integrate it ahead of whatever time I have, because I want it to penetrate, because unless it penetrates the ground, I cannot have the detect condition. So what I need to do is, to fix this, I need to change my time. Let me just change it to 8 seconds, okay, and just run this. So now you'll see that the leg actually penetrates the ground. Okay, so the intention of doing that is because unless I have penetration, I cannot do detect contact, because what happens if it doesn't quite make contact with the ground? So this is good. Now let's try to change the event so that it will actually touch this and not penetrate the ground. So let's go to one step. Let's get to remove those events and make it ready. Let's go to contact. I pulled out θ1, θ2. If you remember from the notes, I said that the condition is θ2 plus 2. Okay, I think I did a mistake in my notes. Notes had an error. I said the condition is θ2 is equal to 2 θ1. Okay, that's not true. It's actually, the correct answer is θ2 equals minus 2 θ1. Okay, and that's just because the convention, you remember when we started this off, it should be θ2 is minus 2 θ1, or θ2 is minus 2 θ1 is the right condition. So when you get to the other side, you have θ2 plus θ1. So my bad, but that should be the condition. And then the direction is, well, for now let's just put 0 if it doesn't care of the detection, and then just put 1. Okay, I'm going to show you how this fails. So let's do this and run. You see, it just stopped. It stopped there because this is a valid condition for that to meet theta 2 plus to theta 1. Okay, so we want to tell it to not stop integration when theta 1, in this case theta 1 is close to 0.2. We only want to detect collision after theta 2 goes negative, theta 1 goes negative. So let's say that we'll go over here, we'll say if theta 1 is greater than should be less than so since it goes from 0.2 all the way to negative 0.2, we only want to detect for negative values. So let's put some small value and then say that if this is the case, that is it is in front, then we want is terminal equal to 1, which means stop integration, else it should just continue integrating, continue integration. Okay, so this I need to eliminate because I took care of this. The direction really doesn't matter. You can put 0 or you can put this. Both this say that 0 means that it can take either direction. If you put open close bracket also means either direction. Just put 0 if you think that's better. Okay, just do this and now let's run this. You can see it just went past and it's still interpenetrated, and so there's a problem with this. I think I might have messed up the angle condition here. Theta 2 is positive. It goes from, let's look at some plots. So plot T, Z, I want to plot the first value for the angle and red, and T, and the third value, which is the theta 2. So I can say legend theta 1, theta 2. Run this and we'll say this is figure number 1. Okay, so this is the theta 1 and theta 2. So you can see that theta 1 goes from a positive value to a negative value, and so I actually had this condition wrong. So I want to detect the collision when theta 2 is 2 and so on. I don't want it to be positive. So let's just think this will fix it. Okay, I did not do the animation. Let's just turn the animation on. Let's comment this out. My bad. What's the problem? Huh. Did I switch this? I believe I switched this. I have a feeling that it's a grazing collision. So grazing collision happens when the foot is going along the ground and just grazes the surface. But before that, let me check this. I think this is wrong. This is not right. Let's just try a different initial condition. So to avoid the grazing collision, so let's just put let's say 0.2. So now you'll see that the okay just doesn't make it through. Let's try minus 0.25. Okay, that was also not fast enough. Let's try 0.28 because 0.3 was too fast. Okay, that's better. If you see the foot of the the swing foot, it actually was above the ground. That's not going to give me a grazing collision. So I just need to take care of the condition now. I think I made a mistake here. Oh, something is not right. My condition right, theta 2 plus the theta 1.
Professor, should you be taking the difference between the two angles when theta 2 minus theta 1 is very small?
You mean this should be negative?
Or no, I'm saying for your condition, your
This,
Boolean condition.
this one?
Yeah, what I, I, I could be
Yeah,
wrong, but isn't theta, we initialize theta as a positive value, so it's certainly not the stop condition, right?
the stop is right. The stop is when theta 2 plus 2, that's correct. But here I'm trying to avoid, so here it is stopping in this condition, which is clearly not we want.
Right.
So we want it to stop when this leg, the stance leg, is on the other side. And since a convention is when the leg is in the initial phases, it's positive. And since it's at the negative velocity, it's going toward the right. Its velocity is negative, so it's going to become more and more negative. And the condition here is saying that when the theta 1, which is the stance leg, is on the other side, greater than minus point, I think it should be less than minus 0.05, which means it's more negative. It should stop.
Mhm.
Otherwise, it should just continue. Uh, I thought that was right. It doesn't stop. Unless I'm doing some mistake over here. Oh, yes, I'm doing a mistake here. This is not the second item, it's the third one. Because I have theta 1 dot, that's z2, and this should be z3. Okay, so now I think it should work. Let's hope it works. Okay, now it detected collision right there, which makes sense, but it's not the thing we want. I think I'm doing some mistake here, switching these things. I need to look at it carefully. I'm just now pretty much guessing. There, it stopped there. Something is not right. Okay. Is it this? So in my example code, I put that for this direction. Nope. There's something I'm doing incorrectly. My code says I should do, if it's greater than, that means it is, if it's greater than, it means it is pre mid stance, or mid stance is when this is vertical, so that's before mid stance. If it's before mid stance, then you should not stop integration. Other than that, you should continue. That's what I have in my code. Let's see if it works. Yeah, I stopped there, which is not right. Okay, we are way past the time. It's 2:30. I'm hoping I'll get debug this and then we'll stop. Theta 1 is right. Theta 2 is right. Contact is all right. This is stop integration. This is continue.
Professor, is the thetas are with respect to the vertical, correct?
Theta 1 is with respect to vertical, and theta 2 is the angle made with the other leg. So this is with respect to vertical, and this is the angle between the two legs.
So your condition uh, for when it stops or continues in the now, theta 1 greater than negative 0.05, that just relates to the angle of the stationary leg, or not stationary, but
The stance, the leg on the ground, yes. So whenever this leg is past the vertical position, which is this, sorry, it's before the vertical position because negative, the positive values are before the vertical. I say that you should just continue integration, otherwise you should stop. I can change this to minus minus
I, yeah, so I think so we don't want it to, we want it to stop once there's collision, and the condition for collision is when uh, theta 1 minus theta 1 is equal to theta 1 minus theta 2, correct?
It is basically theta 2 equals theta 1 minus I think theta 2 is the angle between the legs.
Mm-hmm.
That should be equal to, no, the, my bad, theta 1, which is the angle between the vertical and the stance leg, should be the same as the angle between the vertical and the swing leg.
Mm-hmm.
But then there's a, yeah, that seems to be right. Which, but then there's a problem with the sign here because the way I've defined the angles, this should be negative of that one. And that's why you end up getting this condition. So this is not, this I'm sure it's right.
Then I may be misunderstanding the code, but isn't is terminal condition, wouldn't it be not when theta 1 passes 0, but when theta 1, or not when theta 1 approaches 0 from either direction, positive or negative, but when theta 1 approaches half of theta 2?
No, so this is a code to avoid detecting collision like this instance. It means,
Oh, I understand. Okay, sorry, I was misunderstanding what.
so it does detect collisions whenever this is true, and that happens at least three times. It happens pre-mid stance like this, what I have here. It happens approximately at mid stance when the legs are parallel to each other, and happens
Right,
after mid stance. I'm just telling that avoid looking at those instances before mid stance, only look after mid stance.
right. Okay, so I was sorry, I was misunderstanding what the is terminal statement was.
I
I
see.
mean, I understand now. Sorry.
Right. So that's weird. Okay, there it worked. Uh, so I need to launch the other leg with some speed. So I just put 0.1, but I could put 0.2. So that way, this is the swing leg speed. So now if you run this, it goes. So you can see that that is like a bad way. I don't want to
Mhm.
detect this condition. This is not when you want to detect it. Now, in real life, there's a foot and there's a knee, and so you can bend a foot or bend a knee so that you can avoid the stubbing. But with these walkers, you always get a stubbing issue, which you want to avoid in code. So it's non-realistic in terms of simulations, but you're really not focusing too much on the stubbing part. You're just focusing on the dynamics. Um, this is weird. This is greater than minus zero point 0.1. The condition I have is 0.5 on in my notes. See, it shouldn't stop there.
Is that because in this case, with these initial conditions, the moment at which the legs cross, they are not vertical? So they are
Yeah.
at an angle greater than 0.05?
Yeah, yeah,
So probably some larger initial velocity would allow this animation to be successful.
sure. Like try 0.28, what I had earlier. Now it gave me you there, so it just failed there, but it's a problem here. That's weird. So this is what I'm talking about when I say getting these things to work is requires a bit of tricky tuning, and here that's not right. Uh, okay, so I think we should just stop, and I'll just debug this on my free time. Yeah. Continue is 0. Stop integration is 1. That's weird because theta 1 now is close to 0. It shouldn't have. Oh, greater than. Why am I doing this wrong? Yeah, that's not right. But theta 1 now is. Okay, let me. So here's how you debug this. Basically, I'm going to just try to write here g stop. And let's say theta 1. And then you'll see what it does. G stop. So this is what it's thinking, 0.2. So here the angle is 0.2. So this is wherever this function is called. So first is g stop, second is the theta 1. Theta 1 is 0.2, so it's there. And now if you look at this condition here, contact, you see that it is actually less than zero point 0.1, and so it actually stopped there. So that it took a few things before it stopped. But essentially it stopped. Now if you change this to greater than minus zero point 0.1 and then run this again, okay, now you can see where it stopped. Here you can see that it's actually detecting that, but it's not stopping. It just keeps going point because you can see that there's a progress in the theta 1 value. It just keeps decreasing. Over here it becomes negative 0.00, let's see, 0.5. Okay, now here it's apparently minus 0.05, but that doesn't make sense because the leg seems to be on the left side. There seems to be something wrong with the animation because now the leg is actually not vertical. It's actually towards the left, which is actually a positive value. So what confuses me now is this doesn't look right in terms of animation. There's something wrong with the animation. The animation is not truthful, I think. There's something I made here, some mistake I did here with the animation. It's most likely here. Okay, we'll stop. I'll continue where I left next time. Hey Jim, also the guy came, I think his name was Tartaro. He came and to check for the sound.
Yep,
But can you hear the sound now?
I cannot.
Okay. It didn't it was he came in person and I was here luckily, and so he there was it was not making this sound, but I can hear the sound now.
Oh, I can hear it. It's a little more faint than usual. If I really concentrate, I think I can hear it.
Well, it stopped. It was just whirling, but I told him I'm supposed to call him the moment it comes, and he will show up, I guess.
Yeah,
Uh,
it might be worthwhile to also like give him the call, but just pull out your phone and try and record it.
that's what I plan to do. Yeah.
Yeah, because it does. He'll be on some project somewhere else, and it'll take him 20 minutes to get over there.
Oh, I see. Yeah, because it stopped now. Okay, looks like Ernesto is here. Okay, let's start. So I already shared my screen. Can you see MATLAB?
Yep.
Okay, so the point of trying to do the simulation real time in front of you is to show you the frustration sometimes in making the simulations work, and I think that most times simulations are easy to do. You copy paste the equations, you just press a button and it goes, but not for walking. It turns out it's kind of hard. You need to get some things just right to get it to work. So I'm just trying to show you sort of the frustration. So last time I suffered, you suffered. This time I actually debugged the code. So I've kept it at the point where I left it last time. I'm going to run the code and you will see animation. And then what we are trying to do is trying to get it to take a step, but it stops there. It turns out that the issue was not in the, so we integrate the equations and we were trying to detect contact conditions. And the issue was not in the contact conditions. They were absolutely right. The issue was actually in my animation. It was not what the, the animation was actually stopping earlier than it was supposed to. And the reason for that was that I basically took the z all values was an input. I interpolated the data points to get a few data points, and then when I tried to do the animation, I used this theta one, theta two, xh, yh. But if you see this xh, yh, I use z all, which is the input, when I actually have should have taken the z interp. So that was the mistake. And so it just happened that the animation stopped at the right time when that condition was also met, and so it gave the wrong impression that the collision condition was wrong. So I just had to put this, uh, and then hopefully it'll work. There it is. That's what we wanted. Okay, so we can I just had increased the speed a bit there. So here is, you see it fails. That's because the speed of the stance leg or the leg on the ground is not fast enough. uh, so we just have to go back to point 2, I guess. So still it looks like it's not going to work. So if I do 2 steps and 3 steps, it's not going to work. Now I have not programmed the simulation to do more than 1 step because I have not included the foot strike condition. So I only put the single stance and collision. So I need to work on that. So if you remember, I took OD45, I took the RHS, which is the single stance, and then I stopped when contact was detected. Now what I need to do is I need to enforce the condition that uh, there's a foot strike, in which case the front foot becomes the new stance leg and the rear leg becomes the new swing leg. And I had derived a condition for that, and I just need to copy paste that and go from there. So let's get that condition from the derivation. So let's see. What's MATLAB? Okay, so this was the derivation. Okay, so what I did was I ensured that all the foot strike equations start here. So I need to just essentially copy paste this. So make a new file. Let's call it function z plus, indicating it's the instance after foot strike, and we can call it foot strike. Like the input is z minus. Okay, that's all the state variables before foot strike, and so we can copy paste that. Okay, so we need to tell MATLAB what these things are. Okay, so first let's try to set those up. So first of all, let me pull up my notes. So I get this right. Okay. Okay, so let's start with plucking up values from z minus. So we have theta 1 negative is z minus 1, theta let's see, I think I used omega, not theta, for omega for the speed, and I'll get an error if I don't. Yeah, so I use omega 1n and omega 2n. So let me just stick to that. So I'll call this omega 1n equals z minus 1, sorry, 2. And then I need to do the same thing for theta 2. Okay, so I've collected all the data variables. I still need to put the mass and so on. So I already have that in my RHS. Let me open my RHS file. It's right here. So just copy paste this thing. Okay. So it doesn't require G, clearly the slope. Looks like that's all I have. Okay, so once it does that, I need to assign to it things like Z plus, which is going to be my new theta, my new omega, which is by the way omega 1, new theta 2, which I have not assigned yet by the way, and then that. So remember I told you what theta 1 and theta 2 is. It's basically theta 1, which is the velocity after foot strike, is going to be theta 1 negative plus theta 2 negative. This is just swapping the legs and so on, and so the angle swaps, and then the hip velocity gets negative of the earlier ones, should be theta 1. Okay, so this will return to me z plus. I just have to take this and then paste it in PWB. No, sorry, one step. Okay, now this z minus is only the final state, so I need to say z minus equals z end. Okay, so then that z end will go, and then it will become z plus, and then we can print this just to see what it is. So z plus, and then let's take what the initial value is. So remember that we start at a certain instant, the Poincare section, at just after heat strike. We do the integration, then we do collision detection, foot strike, and z plus should be same as z0 for it to be periodic motion, and that's what we're trying to do. So I am going to do this, and I'm also going to uncomment something here. I have in my collision contact condition actually had something which was printing. Okay, so now it's only going to print two things, z0 and then z plus. So let's go here and run this. Okay, there's a problem. Walker.i. Okay, so I did not, it doesn't know what walker.i is. So let's just look at foot strike. Okay, so I need to pass walker. So I did not pass it. So let me just pass that, which means I need to go to main and then pass, sorry, one step and then pass walker. Okay, I hope it will work now. Okay, so this is actually a good way of seeing it. So you have the initial condition. After one step, this is the state. This is the angle theta 1 dot, theta 2 dot. So ideally we want this z0 should be equal to z plus for it to be periodic motion. You can actually see that z plus is actually twice negative 2 times z theta. It's exactly the same as this, which is theta 1.2 is negative 2 times theta 2. Okay, so there is a discrepancy. So what we can do here is we can just play this game where we are trying to perturb the system, right? Try something else. Maybe try 0.19. Okay, run this, and now you get well, it takes a step, and you can see this, it's getting closer, this is getting closer, and then you can just keep trying to do that. 0.8. I mean, there are 4 things to vary really well. 3 things here, because this one is always minus 2 times theta 1. So you can try that, and so you can see it's getting closer, fairly close. This seems to be a little far away. Let's just fix this. 0.1 maybe. Okay, so we can just keep playing with this, and this may just work out because it's a small system, but you want an automated method of generating this z0 such that after one step you pretty much get z plus to be same as z0, and this is where we can use some of the tools we've used for inverse kinematics. When we did inverse kinematics, we were trying to solve for roots of an equation. So here in this case, the roots of the equation are uh, uh, the equation is basically that after one step z plus should be equal to z0. So instead of guessing, let's just try to see if we can use fsolve to get z0 such that z plus is the same as z0. So let's do that. Okay. So this is basically a simulation of everything else. And this is our plots. And then this is animation. Okay, so what we want to do is we don't want to quite simulate. We know that these values are in the ballpark, okay? And I can tell you that it's kind of important to be in the ballpark, because if you're not in the ballpark, then the fsolve has a hard time to get the solution, because fsolve is based on gradient methods, and gradient methods like Newton-Raphson, if you remember, Newton-Raphson is used to find roots of an equation, are good when you are sort of close. You don't have to be very close, but you have to be close. You can't put 10,000 for the theta ones and so on and expect it to solve. Okay, so we did that. Let's just comment this because I'm not interested in doing all this. Just delete this. So what I like to do, instead of commenting out, just put a if condition, put a 0 so it's never executed, and so that will not execute. So let's do root finding. Okay, so let's just do that. So what I'm going to do is I'm going to use fsolve. Fsolve. So say help fsolve. I take the simplest example and copy paste it if you can find one. Yeah, that seems to be good. Let's take this, copy paste that, and then modify this. In this case, we want some distinct function. You know what, I'll use, maybe I'll use this one. This seems to be a better example. Just use one of the two. Basically, I don't want it to be inside here. I want to define it externally. So I want to use something like this. So I'll use these things as a reference. So our input, I like to put this separately. The noise is fine. Maybe my computer is spinning really hard. So I think it's that. The fan is not rotating. So Jeremy was asking on chat. Z equals, sorry, options equals that, and then I like to put it like this way. It's a much cleaner way of doing things. And then since it asks for initial guess, in this case my initial guess is simply z0, and then I like to call that z with a star, but we call that z star, which is the fixed point. Okay, so now I need to pass z, so I need to say let's call it fixed point. The inputs are going to be x. X is, I believe x is a dummy variable. You can give any name to it, comma Walker. That's all. So we need to write this function for it to work. So let's just write that function. Okay. So function fixed point Walker. Let's call that z. Okay, now the beauty of creating that one step is that the one step function has made our life easy. All we need to do is call one step with input z, and let's see what one step requires. So one step requires t0, z0, and Walker. Okay, so let's just put it that way. Let's go to fixed point. This is the syntax needed. Now let me save this. Fixed point. It requires t0. So let's just say t0 is 0. And then z0, which is basically this one, this is going to be our input, and then walker. And then since we are solving for root, so one step basically takes the initial condition z, integrates that, does collision detection, does foot strike, and gives us z plus. And we want basically z, which is the input, should be the same as the state after one step. So if you like to think of it this way, this is z plus, right? And z is the initial condition. Then we want z minus z plus should be equal to 0. This is what we want. So the way fsolve works is we say this is f, or we can call that f is fine. And then we say that f equals fixed point, which means that what fsolve is trying to do is trying to set f to 0, which basically achieves our objective of setting z equals z plus. So this is the fixed point condition, fixed point function. And it is made it easy by using this one step, which is this building block we talked about. And let's run this and let's hope it works. Okay, it's printing those values because somewhere I actually didn't comment. So I need to comment this, and run this. Okay, so it basically gave me some roots. But you know what? I don't know if they converge or not. So let's do help fsolve and see what the syntax is. So if I want to find other things about fsolve, which is fval, which is right here, which is the value at when it terminates, basically gives you the fixed point or value of f, capital F, and then exit flag. So I want to always monitor the exit flag to see what it is. So let it print exit flag and then print z star. Okay, so that's bad news. Help fsolve. Fsolve exit flag -2 means converge to a point that is not a root. Okay, so we have a problem. This is not giving me the root I wanted it to give. So we need to debug this. Let's see what fval is. Okay, let me know if you have any suggestions. I'm going to try to debug. I've not coded this, so it's been a while since I coded this. So I don't know what I'm doing wrong. So here is the problem, which is if you look at fval, it's throwing out like an array. So there is a clear problem with what one step is outputting. It's giving me an array and it's trying to do z minus z plus, which is an array. So I think I know what the problem is. When I make one step output z, it outputs every possible thing from OD45 when I only wanted it to output the last value. So what I need to do is I need to say, I need to basically tell it to output z plus. Okay, so if I change that to z plus, I think it'll work. Let's see. Okay, so you can see that it actually gave me exit flag 1. It said z star. This is apparently the fixed point. And then the fval is basically the tolerance. It's 1e negative 8. Okay, so now if I want to simulate it, so since I found a root, I want to simulate it. Let me uncomment this and this. Or you know what, let me just, the easier way is to just make it 1. Okay, run this. Okay, now there's a problem here, which is I can get the roots, but I can't get it to simulate. And the reason is that, you know, I've broke my one step. I'm only outputting z plus. I'm not outputting z. Z plus is a single value. So I need to take care of a case where I want to sometimes output all the state variables, all the z's. Sometimes I want to output only z plus. So how do I take care of this? So let's try to see how this output should come for me. One is when I used it for fixed point, okay, in this fashion, it should only output the final state. However, if I used it in this fashion, it should actually output me only the entire state z. Okay, so one way of seeing that is, you can see here there's only one output. In here you can see that there are two outputs. So why don't I exploit that fact to put a condition on one step to do what I wanted to do, which is, I'll call this z. Okay, so normally it passes on z. What I'll say here, however, is that if so there is something called narg out, help narg. Okay, and arg out is basically the number of output arguments. So it basically tells me how many output arguments are in this, are asked by when this function is called. Okay, so in this case the number of arguments are two, but sometimes I only call I call only one output, sometimes I call two outputs. So I'm going to exploit that fact here to say that if narg out equal to 1, which means that it is this case, then change the z to z plus. So it only outputs the last value. Otherwise, just send z, which is the normal thing. So now let's run this. So it did both, which is basically it gave the exit flag integration, and it also did a simulation. In fact, it also must have done a plot. No, I don't have the plot yet. We fixed the plots. Oh, I'm not. You uncomment this. So now if I run this, it does that. It also produces the plot, which is behind figure 1. Oh, it didn't do the plot. Let's see what's wrong here. Huh. We see z and t. So why isn't it plotting? Let's try this. Oh, there it is, but that's weird. Just comment this. Okay, now it did. Maybe I did not do close. I did close all. Okay, maybe it'll run this time. There was some error. Uncomment. Huh. I believe I'm calling figure 1 somewhere else. Might be somewhere here. I'm calling the figure 1. No. I think I'm calling figure 1 somewhere else, why it's getting refreshed. Let me just do it this way. Figure 1, let me make the animation, and so then we'll first do the animation and then do the plot. And then if you like, let's make one leg red, one leg blue or something like that. So let's just go to animation, change one leg to blue. That looks slightly better, maybe visualization. We can also do something like, so one thing here is, if you want to see how fsolve works to get the solution, I actually like to put display as iter. So it tells you how the optimization or the fsolve is producing the output. Here it's very fast. So if you go here, it actually took about 20 function evaluations, 3 iterations to get the solution. Sometimes you want more decimals than just 4 decimals. So what I try to do is always in the front I put format long, and that actually produces 14 decimal places. So as you can see, it produced 14 decimal places. Now one thing to note is that our accuracy of fsolve is actually dependent on the accuracy of the integrator. Our integrator here is right here. I have set the accuracy to e-10, which means that our root is not going to be more accurate than 9 decimal places. In fact, it's over here. You can see it's only accurate to it's about 9 places. Okay, so if you want to go further, you can just set it to 13. I think 10 raised to negative 30 is about the max you can do. And then you can also set the tolerance for fsolve. I always like to set the tolerance. Let me search for the command for that. fsolve. So the command for that is, if you set it here, if you want to set the tolerance for fsolve, you say that it's negative 12 here because our integration tolerance is accurate to 13. So I'll run this and you'll see that this will change to negative 12 or negative 12, I think, or like 11. Oh, there it says negative 14 apparently. Okay, so that's one. You can now play with the initial condition. What if I try zero point 0.3? Okay, so let's note this value first. Let me just save it. So one root is this. Now let's play with this zero point 0.3 and then run this. So it's, you see it's taking more iterations now. So it did not converge. In fact, it says -2. So just be mindful that you have to check the exit flag. Unless you do that, you're not sure. So this is not a good condition. Let's try, let me change this to 0.2. See what happens. Okay, so that didn't converge either. So these frustrations are very normal. In this case, I actually planted in the code this initial condition, a similar one, and it was much easier to find. But normally that's not the case, and you'll have to find your own initial conditions to get this going. And there are papers written on how exactly to go about finding the initial condition which will work. What I like to do is I try to ballpark the initial condition using animation, which I just showed you, and then once we had the initial condition, it was much faster to uh, get the system to. So here it is, it's failing also. Here it's saying exit flag 1. That's interesting. So here's a case where it's actually saying it worked, but it thinks this is, but actually did not work. This is interesting. I'd never come across this before. So it's always good to check the animation. You can't trust fsolve because sometimes it gives you non-realistic solutions. I've seen solutions where the robot will flip, make a somersault, and then it'll land, and the fsolve thing it's converged, but actually didn't converge because well, it converged, but the solutions are not feasible. You can't get a robot to do those things. So I think what worked for us was 0.18. If we keep it as it is. It looks like I did not put the right one. Maybe it was 0.25. We kill this, Control C. Yeah, that converged. Okay, now the last thing left before we finish this, wind up with this, is to find if this root for fixed point is stable or not. And I said that one way to do it is to use the Jacobian. So I'm going to do the same thing now. Okay, so let's put 0 here. We don't want to do this. We just want to check the stability of the fixed point. Okay, so I will not spend my time writing this code from scratch. I'm just going to copy paste the code I wrote down earlier, but it should be fairly straightforward to see this, how this works. It basically uses the fact that you can find the Jacobian by taking a finite difference, and that's what I'm going to do. And we did an example of finite difference for the Jacobian in one of the lectures. Okay, so this is what I do. I have to write a function called partial dir, which gives me j. The inputs are z star and walker. Okay, and let's see how to, well, and then once I get that, then I have to display the eigenvalue of j, and then let's see what the eigenvalues are. Well, I need to actually take the norm of eig of j. So the eigenvalue is given by the maximum of the norm of the eigenvalue j. Okay, so let's like this partial derivative file. This is like your own user written finite difference. So in the code, I'm going to post here is there are two ways of finding it. I actually have, well, this is a very generic way of writing. You can find a partial derivative of any function. Okay, it doesn't have to be one step. Uh, this one uses forward difference, and this one uses central difference, and then you have to take a perturbation and so on. And I think, so this works. So one reason why it will not work is because one step requires t0. So I need to change, incorporate that here. But let me save this first. And then the thing I'm missing here is one of the inputs is 0, which, so this is for time. The 0 is for t0. Then I need to do it here too. Okay, let's run this. Okay, so this actually gave me all the, well, let me actually do it. Let's do it step by step. This is going to give me j, then eigenvalue of j, and then null. Okay, so this is j. This is uh, the eigenvalues of j, and interesting. So it basically gave me the norm of the whole thing. I just want the norm of each individual line. So let me get that. How do I get that? Okay, so I need to do this individually. So I need to do for I equals 1 to 4 because j size of j is 4. And then I need to do it element by element. So I need to do j. Okay, now it published 4 eigenvalues. It doesn't work. Input matrix must be square. Line 26. Oh, my bad. Uh, okay, I need to do something different here. Ike j, let me give it a name. And then I need to find Ike j, and it should be norm of that matrix, which is basically Ike j. So let's just do this. Okay, so it's printing all the 4 values, but it says answer, and like that. So I put display. That will get rid of the ans answer in the. Okay, so these are, let me put it, test eigen, so norm of the eigen values of j. So when I print this, now it's going to look prettier. So there are 4 eigenvalues. One of them is zero point 0.4, second one is zero point 0.4, third one is 1e negative 12. It's almost negligible, it's almost 0. And the fourth one is 0.31. Okay, now what you will notice is that always one eigenvalue is 0. Okay, and that happens because, and you need to think over this why it happens, but it happens because of the Poincare section. One of the initial condition will map it onto itself because we are in the Poincare section, and so one of them will always be 0 anyway. So but when you have 4 eigenvalues, you look at the maximum eigenvalue, and the maximum in this case is zero point 0.4, and we know that zero point 0.4 is less than 1, which means that this particular fixed point is stable. So since zero point 0.4 is less than 1, the fixed point is stable. Okay, so that's what we want to conclude. And then I'm going to get rid of this now, since we figured all this out works. And now you can get everything, which is do a fixed point, calculate the stability, do animation, do a plot. And so now the code is ready for you to explore. So I'm going to post this, which I developed in real time in front of you, but I'm also going to post another piece of code which I wrote offline, and which has all these things as a single file. Okay, and this one goes a step further, which is basically it can do multiple steps. In this case I put steps equals 3, and the way it's done is, if you look at one step here, one step, I actually have a if for condition which I go from one to step. So really, this is not one step. I should have called it maybe n step because it simulates n steps. Okay, so when I run this, what it will do is it will basically do three steps and do some plots.